Okay, well, hi there, everybody. The title of this section of the workshop is called Krustlet, or How I Learned to Stop Worrying and Love the W's. If you haven't noticed from the introduction there's a lot of W's flying around. For some reason, all the acronyms in this space start with W, probably because of the web thing. So just a little funny introduction to that. Let me share that real quick. And just as a warning, this can be a little loud when you share videos, so just by the way.
All right, everybody, settle down. Come on now. Welcome to the weekly meeting of the National Association of W Lovers. We are gathered here today to pay tribute to that great letter, W, and the wondrous sound it makes.
So anyway, there you go. If you haven't seen that before, that's the Muppets from Sesame Street. And someone shared that once when we were talking about this, because there are sure a whole lot of W's in this. So let's go ahead and introduce ourselves real quick as soon as I get the share back, right? So let's get to some intros. So who are we? My name's Taylor Thomas. I'm a Helm core maintainer. Been doing Kubernetes since around the 1.2 timeframe, and Docker since about 0.7. That's just mostly to say that I've been doing this whole cloud native thing for a while. So hopefully it gives you some confidence. I'm not entirely just making things up here. And then I am a Rustacean, or something like Rust. Came to Rust from Go. Those are my social media handles in case you want to reach out on any of those platforms. I'm a former Portlander. I used to live in Portland. Now I'm in Utah, here in the U.S. And I'm loving being close to more mountains. I really like going up those. So that's a little bit about me. I'll pass it off to Matt Fisher to talk about himself.
So hi, everyone. I'm Matt Fisher, and I'm also here presenting on behalf of Microsoft and with Taylor. So I am also, so the two of us together, we're Krustlet core maintainers. We're also Helm core maintainers. I've been a Helm core maintainer for a couple of years now. And for the most part, I think Taylor and I are pretty much equal when it comes to our level of experience when it comes to Kubernetes and Docker. We kind of came around with Kubernetes since around 1.0, 1.1, 1.2, and then Docker playing around at the same time. So we kind of entered the space at the exact same time, I would say. So Taylor's over from Portland and living over in Utah. I'm over on Vancouver Island. I'm living in Canada, and I've been doing that for a very, very long time. Well, since I was born. But you can also find me on those social media handles as well. I'm Bacon Gobbler pretty much everywhere on Twitter, GitHub. Yeah, that's me.
Yeah, so let's go ahead and just dive into a little bit of this. We've heard WASM, WASI, WASC, like I said, lots of W's and the sound it makes. And so this is these are all these probably acronyms you've heard from this beginning section. We'll talk a little bit more about each of them, but we're doing this to give you some context before we dive into the actual workshop, writing code part, about why Krustlet even exists. And to do that, we're gonna have to dive into even more acronyms. So let's go there.
So we're gonna talk about we're actually gonna start with some of the three-letter acronyms from the container world. The two of them that are on the title there are OCI and CRI, and we'll kind of talk about those in a second. So OCI is this organization called the Open Container Initiative, and it basically has to do, when Docker was first introduced, they were kind of introducing this container technology. Well, it was based on LXC and that kind of stuff, but they were talking about this container runtime. How do you run containers? How do you store them? The copy on write file system. How do you upload them up over to a registry in different ways? So OCI was this organization that was formed out of this to kind of standardize those kind of things. And one of them was how do you store it on disk? How do you upload it to a container registry? And so those came out as the distribution specification, the container runtime specification, and all those things. So that's where Rocket and now Docker with the Containerd project and all those kind of fall under the OCI. Similarly, CRI is another standard interface, but this one comes out of Kubernetes. CRI is the container runtime interface, which is defined by a kubelet for how you run a container in a kubelet. And for those who don't know, or are not quite familiar with what a kubelet is basically in Kubernetes, one of the nodes that you are able to run Docker containers on top of. And so there's this kind of communication layer from the kubelet to the container runtime. And in this case, Docker for the most part, or in our case for Krustlet, there's also, we're talking about WebAssembly in different ways. We're kind of implementing the kubelet API. And so that's where virtual kubelet kind of comes in here. Virtual kubelet is this something that masks as a Kubernetes kubelet, but exposes a different kind of provider. So for virtual kubelet, it will run on Azure Container Instances, which is a cloud hosted service, or I believe Amazon, is it Amazon Firecracker is the other service from Amazon that does that. But basically,
well, one of the two.
One of the two, yeah. And basically that's the, it's mimicking what the kubelet API, as in what the Kubernetes API server communicates with the kubelet. The virtual kubelet works as that kubelet. And that's where Krustlet kind of comes in here and what we're talking about. Krustlet does not implement the CRI, it implements it at the kubelet level, and the Kubernetes API server talks to Krustlet in that way. So
the other way I like to think of this is one way of looking at the abstraction layers inside of Kubernetes. And so like OCI, you're talking about low level like shims and Containerd things. That was a little bit too low level for what we were doing. CRI was actually what we tried to do. We had a project, you can actually Google it, called WOK, W-O-K, where we tried to implement this as a CRI, but CRI assumes everything is a container that it's running, and those assumptions made it really hard to test and get around. And so like Matt said, we're at this kind of virtual kubelet level where we're masking as a normal kubelet, even though we're probably behaving a little bit differently under the hood. So that's where that comes from. So that,
oh, go ahead. On that just a little bit as well. When we talk about the differences between the kubelet API and the CRI is working at a very low level of like how to run a container. So how to set up its C groups, how to set up volumes, how to set up its environment and things like that. And some of them are very Linuxy. Some of them are very specific to container runtimes. Whereas at the kubelet API level, when we're talking about it, we're talking about very high level concepts like, give me a pod here, please schedule this pod onto the node and give it a couple of volumes, give it environment variables and things like that. But you're reducing that kind of container or Linux container runtime abstractions, and you're just saying at a high level, please run this workload for me. So it fits in really nicely at that level.
Marcos brought up a good point. Like CRI was initially started, like, yes, by other projects, right? And then it was moved into, it's part of the actual OCI, like, group of projects. You actually find the CRI definition though, like the actual gRPC definition inside of Kubernetes, which is what we were working off of. And so, yeah, that's a good point. Good. Thank you for bringing that up, Marcos. So let's go ahead and talk about, so like, why is it called Krustlet? Well, it's called the Kubernetes Rust kubelet. The primary reason we have it is to run WASM modules inside of Kubernetes, but it's also meant to be used by others who want to write a kubelet for anything else in Rust. So if you wanted to write one for like console, or you wanted to write something that interface just like virtual kubelet does with like ACI or Fargate or any of those things, you could write that. It has multiple providers, and we stole this idea of providers from virtual kubelet. Basically, they're implementations of whatever runtime you're going to use that can be used by the kubelet itself. So Krustlet is similar to virtual kubelet, but our main targets are that we build it in Rust and that it's for WASM. And what I mean by Rust being a target is that there could be good reasons to write like a Kubernetes-centric application, especially a provider in Rust, which we'll talk a little bit about in some of the reasons about how we made this.
Yeah, so when we're talking about why we made this, and particularly in Rust, it becomes really nice when we're talking about security and just being able to compile it in just kind of dense it down into the smallest runtime possible. And then there's also a bunch of different controls that are available inside of Rust, like the borrow checker, that can catch us a lot for race conditions and whatnot. So in terms of just security-wise, it's easier for us to work off the Kubernetes API level or the kubelet API level and to work on this from the security perspective. We get to work from WebAssembly from the ground up. We basically get to understand what's the WebAssembly system interface, where's a WebAssembly module, and then how do we create that sandbox? So then we can say, we only want to allow Kubernetes volumes that have been explicitly added by like a Kubernetes YAML manifest. We only want to mount those into the WebAssembly module. We don't want to mount in other parts. So the security controls around the sandboxing of a WebAssembly module is very strict. And that makes it really nice in that way. We can also do other security controls as well as there are alternative WebAssembly runtimes out there. One's called WASM 3. WASM 3 is an interpreted runtime. So it kind of reads your WebAssembly module line by line and it runs the functions that you want to do. But instead of doing like a just-in-time compilation, it does it at runtime. What that gives you in trade-off is that you can run that on very, very tiny devices. So we've managed to get it working on a Raspberry Pi, but we've been working and experimenting with getting it onto even smaller devices, things that have like only 64K of RAM. So it can only have one memory page of WebAssembly. Those have been fun little controls that we've been trying out. And I know that the actual core maintainer, he's from Blink. He's been experimenting with different devices, and we've seen like Photon red boards and different, or yeah, there's a SparkFun red board, which is like a Photon, and then there's a bunch of other different boards that have a general amount of memory. They're mostly running on like ARM Cortex M0 chips, so always fun for making them really dense. The other really big advantage for us when we were talking and playing around with WebAssembly was this concept of actually running everywhere. When we're compiling applications over to WebAssembly, it's a binary format that we're able to actually execute because we're targeting the compatibility layer at the browser. When we're talking about the WebAssembly system interface, and we'll talk about that a little bit later, it targets the basically browser compatibility for a lot of the things at the operating system level. And what that gives you is a good level of abstraction where your application can run at that level and you can abstract away like the Linux kernel and things like that, which has been kind of difficult with Docker containers, because if you want to run a container that's been compiled to Linux AMD 64 or something like that, you can't run it on an ARM chip, or you can't run that on Windows. You have to recompile it for Windows, you have to recompile it for ARM. So when you compile your application to WebAssembly, we're actually able to run it on Windows, Mac, and Linux, just as long as we have the proper runtime for it, like WASM time or WASC host or things like that. So it's really nice there. And yeah, again, like the smaller footprint for embedded devices is quite nice.
And it's really important to note here, like we aren't, the idea of this is not to supplant Docker. There's plenty of workloads that work better in Docker. And even if everything was in place for WASM and WASI to like actually port everything over, it wouldn't even necessarily be the best decision. This is more shooting for those greenfield things, because like Matt said, Docker isn't actually work anywhere. If you're running actual Windows, like if you're running a Linux a container that's compiled with Linux stuff, it runs on a shim VM that's running underneath to be able to run it on a Windows machine. And there's Windows containers, but then those Windows containers can't move around. And so the run everywhere aspect of this is something that's was something that Liam mentioned at the very beginning, and something that interests us a lot. So that's kind of the big reasons why we made this. But let's talk about like what's actually in here. So this next slide is what I like to call the let's be clear, this project is still very new. So this kind of lets you know like what is there and what we're missing. We have all the basic pod lifecycle things in place. So you'll see it spin up and pull the module from a registry. It has like the downward API support and environment variables. There's also host path, secret, config maps. If you're not familiar with Kubernetes, like this might just fly right over your head. That's fine. This is just if you are familiar with Kubernetes, which I'm assuming a large majority of the audience is. These are some of those features. And also, We have Mac, and as of yesterday, Windows support, Linux, and ARM support for Krustlet. The things that we are missing here are that we have cloud provider volume types that are missing, so you can't do you can't pull in something from whatever cloud provider you're on without manually wiring it up. And we don't have an eventing in place, and there's some networking gaps, which we'll talk about in the next slide.
Yeah, so when we talk about these different WebAssembly runtimes, we kind of discuss about how Krustlet works at a level where we're running a WebAssembly module, and that's about it. But when we talked about it, like with virtual kubelet and things, is that there are these concepts called providers. And what a provider actually means is that it is a way to execute a WebAssembly module on a different runtime. So for example, we have 2 providers currently available inside of Krustlet. There are other providers out there. I know Kevin Flansburgh, who's been a big community member. He's been working on an OCI equivalent one, basically kind of re-implementing the kubelet in Rust, which is really cool to see. But then there's also the WASM 3 provider, and those are kind of like community built ones. But the ones that are the 2 main ones that we kind of talk about with Krustlet is WASC and WASI. WASC, and you'll hear about this as well with Kevin's talk later on. WASC is this kind of actor model system where you can build modules as actors, and then you can build other modules as capabilities, and basically they can be hot swapped in and out. And this kind of gives you an ability to do host calls or external host calls based on those capabilities, and you can provide them there. Because of this, you can actually circumvent some of the limitations right now with WebAssembly system interface with networking support, because you can provide a capability provider for communicating with a database or communicating with a message queue. You can communicate with a logging provider or a backing file system store, like for example, S3 or something like that. So as long as you have an actor and it's bound to the right capabilities, and those are built into the Krustlet, you can have that capability built in. So, and then along with that, it has a very strong kind of unique security model on top of normal WebAssembly modules. The actors that you build are the WebAssembly modules, your application. If you build it, you have to sign off on capabilities that it can actually communicate with. And it also has different ways to like restrict either read or write permissions in terms of capabilities. Like you can say the actor can only talk to the capability, but it cannot receive host calls from the capability, or it can receive calls from the capability, but it can't send off calls to the capability. This becomes really nice when you're trying to interface with a file system provider, for example, and you only want to read data from the capability, but you don't want to send off any data from the capability. So no malicious attackers can take over your actor module and start writing data to your directory or anything like that. So that's WASC. WASI is the kind of, it's the WebAssembly system interface, and it follows the standard. WASM time is kind of the reference implementation that's been written by the Bytecode Alliance. And so inside of Krustlet, what it basically is we've embedded WASM time inside of there. So whenever you want to run a WebAssembly module, it will run it under WASM time. And so we've interfaced with that. It doesn't have networking support at this time. I know that there are proposals out there for that kind of stuff, and that becomes really critical for a lot of workloads who are interested in kind of communicating in and out of Kubernetes pods. But for right now, we're like in a proof of concept stage. We're having a lot of really good fun, kind of learning through some things. And then it's not a full runtime, at least how we particularly use it. It's not necessarily. Do you want to talk about this one a little bit, Taylor?
Yeah, I think the way to say this is that WASM time actually is has like a whole host system that you can run multiple like modules in or call multiple modules from. We're not using it that way inside of Krustlet. So WASC is actually can do even more outside of Kubernetes, as it's a full like host runtime system. And you'll even see some of the cool advanced like networking features that it has a little bit later with the stuff that Kevin is doing. And so as you do something with WASC, you just have to know that you're buying into the ecosystem. You have to use the signing tools, and it has a kind of different application design than a normal like Kubernetes pod and application would use. So it's just something to be aware of, but it has some very cool features around that. Whereas WASI is just, we're using the WASM time code to run a module as long as it needs to run, and then it finishes and we get the data from it. Like that's all that's happening there. We're not like sending it into like a whole nother like host. We're essentially having a host in big air quotes per container in a pod. And so it's just a different way of running it. And so we just wanted to call out that that's the difference between the two. So yeah, the WASI one just follows the WASI standard along with WASM time, and WASC has all these additional capabilities and security things that go on top that we've connected into Kubernetes, but you can also use outside of Kubernetes. So those are kind of the differences between the two providers. And I mean, another thing to note here is we're always looking for people to write other providers, whether they're WASM related or otherwise. Like Matt mentioned, we have a community member who's written one in OCI. Matt has also written one using WASM 3, which is a runtime for, which is optimized for embedded devices. And so if you want to write one, like it's completely open. We have the API defined, and we're pretty clear about, even though we're still like new and there's breaking changes, we're pretty clear about those breaking changes. So that's kind of in a nutshell about what these different providers are. We're mostly focusing on WASC today, but those are the two ones that we have implemented like inside of the Krustlet project itself. So with that, do people have any questions before we dive into the actual writing code and workshop part of this?
And I think we have unmuting possible out there. Moderators, do we want to allow participants to unmute themselves to ask questions at this time?
YOLO.
All right. Yep, so we got that. So feel free to unmute yourself and ask a question away.
You can also ask in chat if you prefer not to talk. Okay, well, methinks everybody wants to get to code. If you have questions, feel free to drop them in. We will send out the slides after, or you'll see this in the video. We have some references here on some more context and ideas about why we chose Rust, why we did Krustlet, how it works. There's links to WASC right there in the actual Krustlet project. So we'll send those out later as well. So now we're going to go ahead and go into the workshop. And this is going to be something that you're going to be able to follow along with in your editors, editors of choice. When we come into this, we're anticipating that you looked at some of the introductory material to get an intro to Rust and how Krustlet works, but we'll have help available as we work through this. So I'm going to stop sharing and pass this off to to Matt. Sorry, we have multiple Matts with where we work, and so they all go by their last name. So if I say Fisher, I am meaning Matt. So we're going to go ahead and pass that off to him, and I'll be working along with him to kind of show what's going on.
Cool. So I'll go and share my screen here, and we'll kind of get started working a WebAssembly module for WASC from the ground up. So can everyone start seeing my screen? Can everyone see the GitHub repository?
You want to zoom in a little further, Matt.
A little bit further. Okay. So this is a good frame of reference then for figuring out what kind of zoom we need. So when we're talking about Krustlet, we're talking about running WebAssembly modules. And there's, again, we're reiterating, there's two different projects inside of there. There is the WASI runtime, and then there's the WASC runtime. Because Kevin's demonstration, we're here for WASM in the cloud, we're talking about WASM Dome. We're going to kind of focus on WASC in particular for today. But you're also more than welcome to go to Krustlet WASI. There's documentation that's available inside of the Krustlet documentation that goes through introduction, topic guides, how-to guides if you want to kind of get started playing around with Krustlet. But I'm going to assume that you've went through some of the introductory material just to kind of get familiar with the system and run Krustlet. But if you haven't done that, that's okay. You can just keep on following along here with what I'm doing, and then we'll just, you can catch up or do whatever you want afterwards. And again, this is recorded material, so we can use this as learning material later. So I'm going to open up my code editor here, and let's see. Let's see. Is that a good size, or is that a little bit too small?
It's looking good to me. If we need to increase it, we can do that later too.
Okay, cool. So we're going to start from a completely brand new project that we haven't done before. We're going to start writing a WebAssembly module completely from scratch for the WASC runtime. So to start building out any kind of module or start building out any Rust project in here, we're going to assume that we're running on Rust. You can use any other programming language that can currently compile to WebAssembly, like assembly script, C, C++, or other possibilities as well with Clang. But for the purposes of this demonstration, because we're already in Rust, we're going to demonstrate building a WASC actor in Rust. So you will first have to need the project called Cargo. Cargo is Rust package manager, and it's kind of also your bootstrapping tool for getting started building a Rust project for the first time. So to start a new project, I'm going to do a cargo new. And because we're in WebAssembly, when you run code inside of there, it's a whole bunch of different functions. And basically the WebAssembly runtime is invoking those functions. It's not like a self-executable or like a terminal command where you say like echo hello and echo is that executable. Instead, it's just a set of libraries or a set of functions that are inside the WebAssembly module. So we're going to be using the lib flag to start bootstrapping a library. And that's where we're going to start building out our WebAssembly module. So we're going to call it uppercase. So what we're going to demonstrate today is a very simple application that listens on a HTTP server or on an HTTP service, and it will listen for requests. And if the query string is lowercase, it will expand it up to a very large size or to uppercase letters. So the first thing that we need to do, and first things we'll see here, when you do a cargo new with --lib, you have your cargo.toml, you have your gitignore, your cargo.lock, which is like your lock file after pinning all those dependencies. Target is a directory that is built with cargo build, and then you have your lib directory. The lib.rs is where we're going to put our actual application code. But the first thing that we need to do is we need to declare our dependencies. And to do that, we go inside cargo.toml. So you'll notice cargo is already self-generated a bunch of information that's useful for here. So like the uppercase is our name of our package. It's version 010, my name and author. And then we also need to add a list of dependencies. So to start off, we're going to need 3 different dependencies. When we're interacting with WASC, we need to have WASC actor. WASC actor is an SDK for communicating as an actor and being able to handle certain events inside of the system. And WASC codec. WASC codec is another crate that's available. Actually, I'll show that here too. There is a package or a website called crates.io. Crates.io is kind of like Rust's package manager and discovery engine. So you can take a look at different packages. And if I go and search for WASC in here, you can see there's a ton of different available, like there's the WASC actor package, WASC host, which is quite useful for when you're actually implementing your own runtime. So for example, Krustlet uses the WASC host package quite often to interact with the system. And then you have a whole bunch of different capability providers that are already provided by other users, which is S3, Redis, logging, Nats, and all that kind of fun stuff. So we're going to need the WASC actor package, which is version 0.7. We're also going to need WASC codec, which is also version 0.7. I know that one of these have been, or sorry, 0.7. I know one of these have been bumped up to version 0.8, I think at this time on crates.io. So WASC actor is 0.7 and WASC codec is 0.8.0. But for the purpose of this demonstration, I have been kind of testing this with version 0.7. So we're just going to use that for this demo. And then the other part of it is Serde. Serde is a package that provides serialization and deserialization from like JSON or from YAML or different things like that. So it's a very useful library when you're dealing with HTTP servers where we want to serialize and deserialize the data as JSON objects. So we're going to use that. And we're going to expand this information because we want to enable a certain feature. We don't want to enable other features that are part of the CERT package. So we're just going to say 1.0 is what we need for CERT. But then we also want to enable a certain feature. In this case, we want to enable the derive feature. So we'll kind of dive into this in a second when we get into the actual package. So there's our cargo.toml. If we compile this right now with a cargo build, it would give us everything that we want to do. So this will compile everything. We get our dependencies, make sure that our dependency tree is all right. Everything else, this may take a little bit of time. So if other people are following along, feel free to kind of show up, or we'll wait for that a little bit.
Yeah, this would be a great time to drop any questions in Slack or the Zoom chat, because we know there's a lot of things here. So we're just giving you some time right now to kind of catch up if you're following along with writing this code. You'll have to, like, there's a lot of different pieces here, especially if you're new to Rust, but fairly simple.
Matt, would it be helpful for you to paste this code into the Slack channel?
Oh, yeah.
Yeah, like maybe just do a comment in there, and that way people can cut and paste. I'd hate for someone to feel blocked by a mistype or something. Maybe periodically you could stop and then, repaste in, hey, here's where I am till now.
Yeah, so I'll just post it here. So if you're in the WASM in the Cloud Slack channel right now, I just posted in the WASM in the Cloud channel itself. But there's the cargo.toml. So feel free to copy and paste that code if you would like. I always express that it's nice to kind of write by hand to get a better understanding of everything. Something I learned from university and from Brandy, my wife, who's currently going through a veterinary technician program, is writing out everything in the textbook actually commits things to memory. So I love copying and pasting code for samples, but it's also a good learning experience too. So either way, whichever way you want to do it. But we can see that the uppercase package has been compiled and everything's there. So all of our packages have resolved and everything's good to go. So now we can actually go and write some code here. So we're going to go into the source directory, into the lib.rs. And if anyone knows how to remove these like little mini annotations on here, I'd be happy to know about that. It's a little bit distracting, but I can move on through without it. So for the lib directory, or for the lib package, we're actually going to write the WASC module. So what we need to do when we're talking about WASC, we're talking about an actor. And when we talk about an actor, we're talking about handling events. And there's actually a fantastic website that's been written by Kevin Hoffman, Liam, and a couple of other engineers over at Capital One who are working on this. And there is a tutorials link in there. We're kind of going to follow through this just a little bit, but using our own custom code here, of course. But if you want to have some further learning material afterwards, this document about creating an actor project, signing the module, creating and running the host is all really fantastic material to go through. So I would highly recommend this because this talks about some of the concepts that we're going to discuss here, like utilizing the HTTP server capability, signing the module, and then actually running it. But we're going to take it a little bit of a step further, and we're going to run it and push it up to a container registry, and then we're going to run it with Krustlet. So a little bit of learning material for you. But back to this. So when we're talking about this again, we're talking about the actors and the events. So first we need to include a couple of packages. And so when we first did the cargo.toml, we used the WASC actor package. And then we're going to call this actor. This is kind of a nice type alias inside of Rust with the as. I think it's quite familiar for people who are with Python, and I think Go also has one as well. I think many different package managers have this way of aliasing different things. It's just instead of having to type out WASC actor every single time that I write it out, I can just call actor. So quite nice. We also need the CERT crate for serialization and deserialization. And then we need the WASC codec crate. We can call it codec if we want. But we've got those three. Now we actually need to include, these are just declaration saying that we're going to include these parts of the package into our code. It's not necessarily importing any libraries at this point. It's just declaring where are we retrieving these crates from. It's not from inside the package. It's not like from another module inside of the source code. It's coming from an external library. So now we need to actually use them. So we use the use keyword, and we're going to do actor prelude. And the prelude library is basically for actor modules. So we use this for importing a whole bunch of different events so we can use them as well later on. But then we also need to use the Serde serialize structure or trait, sorry. This basically allows us to derive different structures and serialize them or deserialize them into JSON, YAML, multiple different kind of formats, so we can do that kind of fun stuff.
One thing to note here too, just if you're new to Rust, is the prelude import is a common pattern in crates. If there's basically a common set of imports that you almost always use, most of these crates or packages in Rust have a prelude module that you can import things from with the star, and it imports in all the common things that you need. So if you're new to Rust, that's what that prelude thing is. You'll see it quite a bit in different projects.
Yeah, and it's used for things like importing macros, which we'll use in a second, importing constants or things like that. So really good kind of not standard idiom to practice if you're interested in writing more Rust. So now we're actually going to define a structure. So first thing, the derive macro or function, actually. Is it a macro or is it a function? Do you know, Taylor? Or is it neither?
Which one? Serialize?
Derive.
Oh, derive is a, oh man. I can never remember the term for it. It's not a macro, I don't think. It's like a config directive, but it's tied. Anyway, someone who knows the Rust terminology better can probably pipe in here. Yes.
Someone in the chat will definitely know. So we're going to use that basically for serializing our object, and we're going to define that now. So we are going to uppercase our objects, but we need to provide an actual structure to serialize and deserialize our data. So we're going to take a query string, and then we're going to return it as JSON in the body. So we're going to return a response. And there's going to be two fields in there. There's going to be the original, which is the original string that we had. So it's going to be a string. And then we're going to have another one, which is called upper. And that's also going to be a string. What we're basically doing here is just kind of defining how this will look in JSON afterwards when we're deserializing. So it'll kind of look like this in, if we're taking text that's like foo, it'll look eventually like this. And we'll see that we go foo. That's kind of like what the JSON object will look like, and that's what we're representing here when we're talking about this original. Serde is nice and where it takes in that information, like the field name, and then upper is another field name, so it'll kind of derive what is the field name from there based on those names. You can override those, of course, and change them using other different definitions and whatnot, but we're quite happy with the lowercase of upper and original in this way, so we're not going to modify that there, but food for thought. Now we actually need to set up the actual events that we want to handle. So we do that using, it's the actor handles macro, and it's curly braces. So the actor handles, this is a macro. And this basically, a macro, if you're not familiar with them, it will basically expand when we compile the code to what we need them to be. And so actor handles is actually just a way
it's actor handlers.
Actor handlers, thank you. Yeah. That's why we were getting a little bit of a red squiggly line there. actor handlers is that nice syntax code, so we don't have to write a whole bunch of boilerplate code in order to handle just how we want to set up a certain event to be triggered or handled by a certain function. So we use this as kind of a nice shortcut inside of the actor SDK. So this is something provided by that prelude include that we were talking about before. So codec. The WASM codec package provides us with a whole bunch of different codecs, like the events that we want to handle. So we're going to be talking about the HTTP handle, and then we need to handle one of two different events. There's the op handle request and the op perform request. When these events come in, op handle request is an event where we have received an HTTP request and we need to handle that. Op perform request is the capability has asked us to perform a request or to send off information, and it will give us the request data, and then we return it with a response and different things like that. But for our case, what we want to do is we want to handle the handle request event. And to do that, we're going to define, or actually it's not that, it's that directive. And we're going to call the function uppercase. Then there's also another part of the WASC actor system that we need to handle, make sure that the actor is healthy. So we need to handle that event as well, which is the codec core. It is op health request. And if you're interested in more in these functions, you can actually look at docs.rs, and I think it's WASC codec. Yeah, so here it is in there. If we're looking at the blob store library, you can see there's op create container, get object info, list objects, receive chunk, blah, 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 blah. But if we go back to the WASC codec one, we can also see there's the HTTP. So there's op handle and op perform, and invoked on an actor in response to an inbound HTTP request, invoked on a host to perform an HTTP request. There are also other things like key value store. These are all kind of like the standard capabilities that are available as part of the system. You can also define your own capability in your own events. So your actor can handle on different things as well. But these are the ones that are available as standards. And there's also like extras, like requesting a GUID, random sequence, and all those kind of things. So again, like the documentation for WASC codec, you can go to crates.io wasc-codec, and you can look inside the package, and you can see there's the home page and the documentation. The documentation will take you straight here. So that's always good to find that. Again, crates.io constantly keeps on finding where I keep on opening my webpage to find out all this information and find the documentation for all the packages that I'm kind of looking at. So now we've handled the actors. So now we actually need to define the functions that we need to do this. The first one, we'll just define healthy. And healthy, the op handle request event takes in a request. We're going to make it hidden with the underscore here, because we're not really necessarily going to do anything. We're just going to say we're healthy constantly. We're not going to do like an upstream check and make sure that everything's okay. We're just going to say everything's healthy, but we still need to handle it. It's codec core health request. And the function needs to respond with a handler result. And the handler result needs to be of just an OK type. So what that basically is saying, give it an arbitrary type. If it's a result that's an error, then that's considered an unhealthy response. If it's considered an overt for us to set, anytime the WASC actor asks us, are we healthy? We'll just say, yeah, I'm healthy. There's nothing else to do here. We're not going to be checking the any databases that they're okay, making sure that like a database table is not corrupted or things like that. But if you wanted to do that, that's also kind of a nice thing to do. If you wanted to make sure that certain directories are okay, Yeah, this is kind of like a semi-useful, making sure that everything's healthy, but don't care about that too much today. The other thing that we now need to do is the uppercase. So this is, again, when we talk about defining this op handle request event, we are returning a function of uppercase, or the uppercase function is the one going to be handling this particular event. So we need to take in a request, which is a codec. It is a HTTP request, and we return with a handler result of an codec HTTP response. Yep. So pretty familiar to most people. You receive a request and you return a response. The capability provider, i.e. the HTTP server one, is the one that actually handles the inbound requests, and then it sends it off to the actor to actually handle the request. So it serializes the data and sends it off over here. I think it's Webpack. Kevin Hoffman might know more about the underlying, how the capability sends this information over to the actor, but last I checked, it was Webpack that did this. Just so if you want to know, but basically the actor SDK is the one that handles all of this nicely for us. So we don't have to deserialize Webpack on the fly. We can actually just deal with very nicely structured requests and responses. So we are going to define a structure because we want to actually return with the response. So let's go let response is equal to the uppercase response, that structure that we defined earlier, and then we need to populate it. The original that we defined there is going to be the requests query string. And we need to, because a query string comes in as, oh, no, we don't need to handle that because it actually is already a string. So it's already in the right type that we need to do. The other part of it is upper, which, yeah, it's upper, not uppercase. Dang, you autocorrect. We need to take the request query string. Oh, you know what? This is actually because of ownership. So this is an interesting part of Rust's way of doing borrowing and ownership. If we borrow twice the query string, we're basically going to run into a compiler error, and I'll show it quickly to you right here. If I do request.querystring.to ASCII uppercase, I think that's all we need to do here. Oh, and a semicolon to define that. And then we need to actually respond. Okay. We are going to do a codec HTTP response JSON. So we're serializing that response as a JSON object, and we're going to give it upper, or response, sorry. This particular function takes 3 calls. One is the payload, which is the response structure of a type T. A status code, which is, in our case, we're going to respond with 200 OK, and the status. Which is just okay. Rust borrow checkers comes into play here, which is great. What we're noticing here is that it's called value has been borrowed here after a move. What that's basically saying is that over here, we have already moved this code or this particular value over to the object, and we're trying to reborrow it a second time. This can run into some race conditions where, for example, if we're trying to use the query string over here, like we're doing r.querystring dot process some information about it. But before that, we did a let r is equal to r.querystring. So we're processing information, we're doing all that stuff over here, and then we expect r to be this original value. It's not going to be because we already processed this value. So this way allows us to say, well, we've already borrowed this value here once, so we don't need, or we shouldn't be borrowing it a second time because it probably isn't going to be expected or what you expect.
Basically, we passed the ownership. So there's and so when you pass something like this, it's now owned by something else, and you can't guarantee that you have proper access to the data or that data hasn't been modified or changed. And so that's what's happening here when you pass the query string first.
So the nice way to work around this is to call toString. What this actually does is that it clones the query string object and it returns back another string. It's basically cloning that, but we're not borrowing the object anymore. We're just passing another copy of that object.
There's actually 3 different functions you could call here. One's clone, and the other one is toOwned, which is saying that you're like going to take a copy of it. All of those would technically work here, but we can use cloned or toString, like what Matt was showing.
Clone actually makes the most sense here. Like toString is nice, but it doesn't actually convey what we're trying to do here. Clone actually shows that we're trying to clone the object and make sure that we're not freaking out the borrow checker. But this is the majority of our code here. So yeah, we've got the definitions of our packages. We've got our uppercase response. We're responding to healthy requests from the actor or from the host. And then we've also got actually handling a request and a response. So like I did before, I'm going to copy and paste this into the Slack channel so other people can follow along here. So we will do, it's lib.rs. And there's that code there. So anyone can play around with that if they want to, and if they're trying to copy and compare what they've written versus what I've written out here. So if we do a cargo build again, you'll see that it already compiles and everything's good to go and everything's hunky-dory. But what that did is that we compiled it as a debug object, but because we compiled it as a library, or we defined it as a cargo library, it's by default, cargo is assuming that we're wanting to compile it into a Rust library, and that's not exactly what we want to do. We want to compile it into a WebAssembly module, right? We want to say that these functions and these handles that we're trying to do, this is a WebAssembly module, so we're going to compile it to WebAssembly. Now in Rust, there's a compiler target available for that. And sorry, if you've worked with Rust for any amount of time, and if you've played with alternative compilers, like you've probably played with a nightly channel or things like that, you would use a project called RustUp. And actually RustUp is the first project that you probably touch because that's how you install the Rust toolchain for the very first time. But RustUp also has a way of you adding new targets or new compiler targets. So we're going to need to add a new one here. I already have it installed, but I'm going to show you the command to actually do it, which is RustUp target add WASM32-unknown. And I'll blow that up. And then I will, again, copy and paste that into the Slack channel. But that basically gives you the new compiler target, WASM32-unknown. That's the target that is defined by Cargo to compile projects to WebAssembly. So we're going to use that target to compile it. But before I do that, I kind of want to automate this whole process and make it a heck of a lot easier on me, so I don't have to remember these like archaic commands. Because if I try and do a cargo build, I might want to compile it as a release object, so I'll add the release flag. But then I'll also need to make sure that it's a WebAssembly module, so I'll have to add the target WASM32-unknown. And that's already a lot of typing for me. So I'd rather run something quite quick and easy, and Makefiles or something that's a lot of people have used, but we're going to use Just. Just is another project that's kind of like a bit of a modern Makefile. It just is a different way of being able to, it's kind of like a script runner in a way, but it has similar syntax to Make. So
and this step is totally optional, and we'll share the Just stuff in a little bit. But it's just something we use to help streamline things inside of Krustlet. So just so you're aware, this is an optional thing. If you don't want to have to deal with installing Just or all that, you can run these commands manually.
Yeah, exactly. by the way, Taylor, how are we doing on time?
So far, so good.
Okay. Sweet. So now let's actually work on a just file. So this kind of automates this whole process. So we can do dev builds, we can do release builds, and then something that I haven't touched on a little bit later, we also need to sign our actor, and then we need to upload it to a container registry. So having this kind of process all automated in one kind of script, or in our case, a just file, it makes it a heck of a lot easier just to remember what commands we need to do when we need to target certain things or whatnot. So let's create a new file in here. Before I do that, let me actually show you what the project is. So on GitHub, Casey is the GitHub username, and it is called Just. So that's the project. Just is a handy way to save and run project-specific commands. And you can see the syntax is quite familiar with makefiles. It's just something that we've been playing around and experimenting with. You don't have to use this if you don't want to. You can write this in a bash script or whatever you want. You can write it in a makefile. Go nuts. But I'm quite familiar with Just, and this demonstration has been written with Just, and I'm quite like it. So we're going to play around with that. But if you want to follow along with this, the installation instructions are here in Casey Just on the installation guide. So you can either use, I believe it's cargo install for this project. There are also pre-built binaries. Oh, actually, there's the packages here. So yeah, cargo install Just will do that for you. So if you want to, since you already have cargo, you can just do cargo install Just, and you'll get that running for you quite quickly. Or you can, if you're more comfortable with doing a curl bash, you can go and do a curl bash for installing Just to your operating system. So that's also possible. And there's also the releases page if you just want to install the static binary. So let me drop. Just keep on dropping these links in the Slack channel. There's that. So you can follow along there. You can get Just installed while I kind of write out this Just file for you all. But the first thing that we need to do is we need to define a whole bunch of variables like we use in makefiles. We need a target. The syntax is quite familiar to like Go template systems, I believe. I believe it's text template, actually. Or I could be wrong. Do you remember? I think it's a Rust project. But it's kind of like mustache-like templates or things like that. But it's quite convenient for writing out things. So the target, again, wasm32-unknown-unknown. We also need to define a debug object or variable, because the directory that we're going to be writing this out to is the debug directory, which is going to be target. So the variable that we've defined here, or it's actually target is target dash wasm32-unknown-unknown plus, oh, you know what? Let's go like this, because I'm going to need to use this later on. So we'll go target dir as a new name.
Probably for time, Matt, you can probably just copy paste the whole Just file from our example into.
All right. Yeah,
chat,
fair enough. It's going to take
time to get people running this on Kubernetes.
So I'm going to play a little bit of a cheat code here. Not the docs. Demos.
Down, up, down, left, left.
Let's do some Konami code to get the Just file. All right. So here's that file. We'll modify it a little bit here. Again, post it here for others who want to play around with it. Copy and paste that. And I'll reduce this size so I can actually write things down. So the target we need to do is, so we're doing, I'll actually run through this quickly. The version that we're defining is version 010. The name is uppercase. Keys, we'll get into that in a second, but that's how we sign the actual actor. Target and release variables are for the debug and the release directories, where again, like that target directory, when we're building them, debug, release, wasm32-unknown-unknown. And because I'm on
that build target to the build and release things. So you do -- target wasm32-unknown-unknown.
Yes, exactly. So we need to do the target, which is going to be target. And then we're going to do what I was just about to do here, which was target dir is that, and then WASM32 unknown. That way we have a nice way of getting the target and also the target directory that we're trying to get. So this is going to be target dir, and this will be 2. So that's the debug release key dir version name. Everything looks good here. So the all target is kind of like if you run just like in makefiles, if you just do that, it'll run this particular target, which is build. So if I just do just variables cargo is not defined. So cargo is cargo, because I deleted that, cargo. There we go. So when we do just, it'll do a just build, which is cargo build -- target with the target. It does not add the release flag in there because we're just building it with all the debug symbols and whatnot. So if we want to add this in a compiler, we can do that. This part we were running into earlier, weren't we? Oh yeah, because we need to do a just keys. So this is the part where we're trying to.
No, it's you have the wrong target directory specified with your variables.
Oh yes, it's. Let's go over that quickly. Do some live debugging. So wascap sign debug, which is the target directory, target plus WASM32 unknown plus debug / the name, which it doesn't look like that is getting the WebAssembly module. So I'm going to do that. I think that's all we need because that should compile the WebAssembly module the way we want it to. Unknown debug, and then once this fully compiles, that'll be on there. And if you see anything else glaring in here, Taylor, let me know. It looks like we're only compiling the D and the RLib. Oh, you know what? I think I might be missing a cargo compiler flag in here, which is important. It was the cdylib part of it. And this is what we were talking about before. So if we go to the demos again. Bear with me a second. Yes, that was it. We need this particular compiler flag, the cdylib crate type. What that basically tells Rust is that we don't want any Rust symbols or things like that. We actually want to make it compatible with the CFFI. And so we don't care about any kind of Rust symbols or things like that. So this particular flag inside of cargo.toml will allow us, when we're compiling it as a library, it will compile into the FFI without any kind of Rust modules. So again, we will do just build again. And there we go. Now we have the WebAssembly module, so we can go and delete that permanently just quickly. But while we're going through that, the account and module targets, I just did a just keys. I kind of flew by that quickly. But this is where in that documentation in wasc.dev for tutorials, it talks about signing the key or assigning the actor. So the first thing you need to do is with these two projects, nkey or nk, new keys. New keys will generate a bunch of different JWT tokens for you to sign your actual module. And then we use wascap, which is another project in WASC, to actually sign the module and sign off on the capabilities that we want it to have. Don't want those in there. And if we do a wascap sign help, it'll show us what capabilities are available by default, which is like the blob store, HTTP client server, key value logging, all those different things. So we can enable those capabilities for this actor. The only one that we care about for this particular case is the HTTP server capability, which is the -s flag, which is why we have that there. And then the -n is give it a name. All right, so we're running into a demo problem here, which is a bit of a bummer, but
You didn't save your just file.
Did I not? Okay. We'll blow past this a little bit and we'll kind of run through what you would do if you had an actual signed module and it was everything ready. So when you are signing the module, you will end up, in this particular case, you'll end up with a project that's called name_sign.wasm, and you'll see that in the target directory. There's an uppercase.wasm, but then you'll see an uppercase_signed.wasm. When we want to publish that to a container registry and actually run that, we will do a project called WASM to OCI. And another link here. WASM to OCI is a project that basically allows you to push WebAssembly modules to OCI registries like Docker, or like a Docker registry, sorry. And it uses the Oros project and a couple of other things underlying, but basically this is how we use or how we publish our modules over to a container registry. To install this project, you can go to the releases page and you can go and find the actual release assets available on there. So if you want to follow through, once again, there's that. Did you find the problem? Oh, maybe that could be it. Okay. But I'll just power on through anyways, and everyone can play around with that later. But so WASM to OCI, if we want to do a WASM to OCI push, that's the command that we would be using to push a module over to a container registry. Then we'd also need to define the module that we want to push. In this case, it would be target wasm32 unknown unknown. We'd likely want to do a release build to publish. So we'd have like the release flag, but I just did a debug one. So we do debug and then uppercase.wasm. We'd want to publish the signed module. So then when we're running the capability, it has all the proper JWT tokens and make sure that it's signed off on these capabilities. But I'll just do this. So it would be like uppercase_signed.wasm is what this would do. And then we would actually give it a container registry that we want to push it to. For this actual workshop, we have a container registry that everyone can push to, if you're welcome to. I think we have to give out those
credentials right now in the Slack channel. These are just ephemeral credentials. It's the Docker command you can use to log in, so that you have like the token there, and then be able to push. This will give you push access. So if you're pushing this, make sure you give it a name that is different than uppercase. You're going to be pushing over everybody else. Just so you know.
So when I'm pushing to a container registry, I'll give it the name of the container registry that I'm pushing to. So for this demo, we have one called Explore WASM. And then there's my username, Bacon Gobbler, and then the actual name of the repository that we want to push to, which is uppercase, and then version 010. So if I had that module, I would actually publish and push that there, but I don't. So I'm going to Control C out of here. But I think I already did this ahead of time. So I already have a module up and available and ready to go. Boop, boop. Good thing for preparing for demos. So the last thing we need to do, if we're actually publishing and wanting to run this onto Kubernetes, we can, again, because this is an actor module, we can just run it with WASC host locally. But if we want to run it on Kubernetes, we need to write some YAML. I'm going to take this from the demo to save time, so I'm not writing out 40 lines of YAML for everyone to see. But if you want to take a look at it, we'll actually go and inspect it so you can see what's going on here. So this might actually look quite familiar to a lot of people who are familiar with Kubernetes. What we're doing here is we're defining a pod, which is like the very basic primary workload that's available on Kubernetes. When we're talking about how a kubelet runs a workload, it runs it as a pod. Even if you define it as a deployment or a stateful set or things like that, pods are usually the primary running type underneath everything. So that's what the kubelet API kind of responds to, is pods. So we give it a name. We can give it any labels if we want to. And then here's the core meat of it. We want to change the registry name to explore.wasm.azurecr.io, and then my username, Bacon Gobbler. And then we call the repository uppercase. So defining here is the container that we want to actually run. In this case, a WebAssembly module. And this is where we actually fetch it from. And we can say a different image pull policy if we want. By default, it's if not present, which is kind of nice in this case. But we can also do it where anytime we restart and rerun the pod, we want it to pull again. So we can do that. Because we're running an HTTP server, we want it to run on a particular port. And then for the purposes of this demo, we want to expose it on the host that we're running it from. So the host port is port 8080. And this is how Kubernetes gets to know that it should be running as a WebAssembly module and not a Docker container. This is all through node selectors and tolerations. So the node selector kind of tells you what nodes can run this workload. In this case, it needs to be a Linux agent. It could be any kind of agent now, because now that we have Windows support, Mac support, ARM support, but early versions of this showed that we needed to have it on Linux. But the architecture that needs to be available for that node is WASM32-WASC. So that's defined in the Krustlet project. And then the tolerations here is just saying that the network has to be available because we need to start up an HTTP server on the node. And then the architecture needs to be equivalent to WASM32-WASC. Otherwise, don't execute it, please. So, moment of truth here. Let's bring this up a little bit. I have Krustlet running available. So I can go into the directory that we created here, which was uppercase. And if we do a kubectl create-f kates, that's the file that we created, that will create the pod. So let's show you what I have here. We have my actual Krustlet is running on my local computer. And that computer name is called Ultralisk because I kind of have a little bit of affinity with StarCraft. So I enjoy those kind of character names, putting as my PC name. But that basically is what Krustlet took as the actual node name, is Ultralisk. So it's been running for about almost 3 3/4 hours, and it's running there. And if we do a kubectl get pods, we'll see that the uppercase, yeah, so I actually didn't push it and publish it. But we can actually run one of the demos instead. It actually exited and did not work. So we'll do a kubectl delete pod uppercase. And then we will go into code Krustlet, and we will do a kubectl create-f demos wasc uppercase, and then it's uppercase wasc.yaml. And that's running. So the exact same service that we were doing before is just already been codified and done for us. So I promise that I'm trying to do not as much of a sleight of hand, but the demo gods do not favor me today. But you can see that the pod is running and is available. If we did a kubectl logs, we get nothing because it's not logging anything, but that's also possible and available for us too. If we do a kubectl get pod uppercase output YAML, we can get all of the different information about it, like container statuses, the last time it was probed, all those tolerations that we defined. And then we can also get things like, is it healthy? Where is it running? And all that kind of information is all available here. We could also do a kubectl status and all that kind of stuff, but I won't run through all that. But again, when we defined the kates.yaml, we had a container and a host port, which would expose on port 8080. So if I went to the same node that Krustlet's running on, the host, I should be able to reach it at port 8080. So if I do a curl localhost port 8080, I will get a response from the WebAssembly module that's currently running in there. And again, that's that code that we were running before. So that's the actor responding to the uppercase request that the capability is actually sending off to the actor. And then the actor is actually handling that and sending it back to the capability to respond back to the user. So if I change this and say, add a new query string of foo is equal to bar, then we'll get the original is foo is equal to bar, and the uppercase version is foo is equal to bar, just uppercased. And of course, if we ever wanted to do something else like bar, it would just handle that. It wouldn't barf out because it's just straight uppercasing it. It's not doing any error checking or anything like that. It just silently accepts all information. So that is all compressed into one little demo. That's all I have to show.
And so this is the point, like, sorry about thank you for your patience as we were working through the little just file things there. It was probably our mistake. So hopefully you can follow along there. We had Ramiro post a corrected just file if you were following along with that. So you should be able to build it and push using those Docker credentials that we passed in, and you can actually run it on your own. So if you followed the intro to Krustlet video that showed you how to get it up and running, you should have a Krustlet node that you can publish it to. Marcos asked a question, like why would you use Krustlet and WASC instead of running like WASM in a standard Docker container? So the idea here is the portability, especially when we're talking in our little intro and giving some context. The idea is that this could be run on embedded devices. It could be run on Windows machines. So the nice thing here is you were running on a WSL on Windows, correct, Matt?
Yeah, I'm running on WSL2 on Windows.
Yeah, so you can also run on just plain Windows. So the thing is that compiled module that WASC uppercase, it will run as is on a Mac, on a Linux machine, on an ARM device, on Windows. It's the exact same thing everywhere, which is very useful. And they're also very, very small. When you compile these out, they're just a few, is it like less than a meg or just a couple megs?
Oh, good point. I think it's only a very few megs, or even like a few kilobytes, if I remember. If you optimize it correctly with like cargo optimization levels, I think like the S flag and a couple of other cargo flags, where you can really optimize the package, you can get it really small, like a couple of kilobytes for a very basic example. But it just goes to show that it can be tiny, tiny, tiny.
Kevin said that if you do optimize, they run less than 1 meg. And then Peter also mentioned about how there's the WASM optimizations too that can be done. And so you can make these very, very small. So there's a couple big benefits there to using them over Docker in specific situations.
The other part of it that I'd also like to point out again was the security aspect of it all. The sandboxing part is really, really nice. With Docker, it becomes really difficult in some ways to sandbox and make sure that only certain directories are readable or writable. You actually have to set up your C groups correctly on the Linux system, so then it can only have access to like certain networking and things like that. Whereas with WebAssembly, everything is blocked off at the very beginning because you just have like the basic runtime. You don't even have access to directories or things. It's up to the host to whitelist those and to give those, or not whitelist, allow list is the proper way to say it now, to actually give those capabilities like mounting a volume or being able to connect to a database in this particular example with capabilities. Those are all sandboxable. It's not necessarily open by default. It's dependent on the actor actually allowing those security controls to be enabled. And that is a really, really powerful thing if you really want to make sure that it's sandboxed. I know there are other projects out there with Docker like gvisor and other things as well. But those are kind of like working at the kernel level to try and emulate what kernel level access calls are being done and then say allow or block those calls from going through. Whereas this one is just like outright, you don't allow it unless it's been allowed at the runtime level. So it kind of gives everyone an even playing field, and you just kind of slowly allow those capabilities into the actual application.
Any other questions? Oh, good. Another question in the chat. The question from chat is, how does Krustlet manage orchestrating multiple workloads? So yeah, it does the allocation inside of the runtime. We're still working on specific, like, for example, how resources and how the limits and things inside a Kubernetes object will be applied. We haven't really like gotten that far yet. We're still, that's one of those things we'll get to in the next few months. But the runtime itself will, we can run as many as we can inside the memory allocated. So basically as much memory as we can get from essentially the heap underneath everything. Yeah, it's not a C groups thing. It's all part of the WASM in general. WASM, you have to explicitly grant permissions to how, like, what they get to access. So like you can't access in WASM time, for example, you have to explicitly, it's called a pre-open file. You have to pre-open like the directory or file and grant specific access to that module to run it. WASC protects everything with the signed capabilities and what it's allowed to access. So Matt was showing the example of just an HTTP server that says specifically to the host runtime, you are allowed to, or you need and you are allowed to use the HTTP server capability, but you can also specify that it can do logging, or that it has access to blob stores, or access to, there's also key value stores. So all those things are done through like the security model of WASC that way. So it's a very secure system that's it's not relying on like specific kernel emulations or things like what Docker does. So it's just a little bit different paradigm.
And then the other part of it as well is that a lot of the orchestration part of it is also Kubernetes in this particular example. Kubernetes is this like container scheduling system where if you have a whole bunch of nodes available inside of the cluster, the Kubernetes API server is the one responsible to make sure that those workloads are healthy, balanced, and running across the set of nodes that are available. So you could have multiple different Krustlet nodes running inside of your actual cluster, and the Kubernetes API server will perform load balancing, or in some cases like resource allocation on a particular node where it has more memory or things like that. And so that's just a matter of, for us, Krustlet actually reporting what's available and what's free, what's been, like what memory has been used, what disk space has been used, and we can report that information back to the API server, and then it can allocate those pods, or in this case, the WebAssembly modules, to the correct nodes that we wanted to apply to through like bin packing or whatever happens to be the scheduling algorithm. So, yeah. Yeah, and like Taylor mentioned with networking, limiting network capabilities per process is kind of interesting. I think that's going to be, whether that's a sandboxing part of it in like the WebAssembly system interface that's going to say you can allow networking or disallow networking. That's going to be a question there, in which case, and then there's also the Kubernetes aspect of it, is like, is there a way for nodes and tolerations to say, we don't want this container to act, or security control context or security context constraints. There's a whole bunch of different security controls inside of Kubernetes to say that you only want this to run with a certain amount of memory, a certain amount of RAM, a certain amount of disk space, and things like that on the volume or things like that. So I would be really curious to see in Kubernetes, because there's a container network interface. I'd be really curious to see if there is some kind of like bandwidth throttling or things like you can do there. In which case we can basically inject the network bridge into the WebAssembly module at some point, but respecting those capabilities that Kubernetes or the user has requested, we can say that the WebAssembly module only has a certain amount of bandwidth it can actually consume. So that's all dependent on the application and the security controls that Kubernetes provides, but then also how we tie that in with the WebAssembly system interface. So there's a couple of different players involved here.